everybody. So sorry for the delay and technical problems with the screens and sound and all that, but the important part is that you are here, and I will show my ukulele tabs in F-sharp talk. So I'm Jérémie Chassaing. I'm come from Paris, and I work for a company, DH, which is part of Accor Hotel. And we are not usually doing ukulele at work like that, but still this talk is about domain-driven design, and especially ubiquitous language and DSLs, and we will do it in a functional way with F-sharp. And the point of all this is to show, we will not talk about aggregates, context, and all that, but we will show how having a clear model in our ubiquitous language, here it will be music, and how to, when we implement it in a clear and simple functional way, we can go really far to solve quite complex problem in a really simple way. So the problem we will try to address is this one. If I show you the tabs for ukulele like that, these are standard tabs. It looks like this. So it's very small because there are a lot of different ones. But the thing is that to play a C, it's easy. You just put a finger on the third, like it's a C major, cool. And a D is totally different. Put 3 fingers there. And then you want to play a E, but it's totally different because it's 3 fingers there. And an F, and a J, and each time it's totally different. What is the logic behind this? How can we write, instead of inputting this data, we could take this data and just have a table with all the chords, but the thing is that as you add more specific chords like minor or sevenths or other type of chords, it will be more data, more complicated. And some of the chords have different ways to play. For instance, you can play E like that, or also like that. There are different ways. Why is the logic behind that? So we will go back to what is the mechanic of music and ukulele, and try to implement it in a functional way. So let's start with a very basic concept. So I will just comment out this one, and okay, let's start. The first thing in music, we work a lot with semitones. So you know there is a C like that, and D like that, but in between there is a C sharp, like that, okay? So each time I change here, I add a semitone to the previous note. So we'll use that a lot in our model. So let's create a type. It's just a measure. So in F-sharp we can define measure, and we will call it ST for brief T because I don't have much time to write a lot of text during this very short presentation. But know that we have semitones, we can use it to define a note. So a note will just be defined by the number of semitones from the C0, which is a really low C. So to define a note, we just define a type, which is note, and whose values is an integer in semitone unit. Cool. Now, we'll need to make some calculation based on that, and we will just add a small operator that we'll be able to use later, which is a plus operator, like plus, and we can take a note N and a number of semitone S, and it will just return a new note, which is this note plus the semitones. Great. Static member. Like that. So this is working. Cool. I just run it for the rest of the presentation. So as you can see, the signature of this, it takes a note and the semitones and returns a note. So this way, if we take like a D and add 2 semitones, we will get a C, we will get a D. Cool. So let's continue with that. Now we can add semitones to notes. Great. But in music, we use a lot something like the same name for different things. Like this is a C, and this is also a C. You can hear? It sounds the same. Actually, it's both C, but one is as one octave, and the other one is another octave. And there are actually 12 semitones per octave. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the same as this one, okay? Cool. So let's write this. We will have a lot of operation with modulus operation on semitones. So we will write our modulus semitone operation, which take value x and y. And the thing is that in mathematics, in computers, when you do modulus on a negative number, we'll get a negative result, which will be totally impractical in our case. So we'll fix that by just doing if x is more than 0 semitone, then we will just return x modulus y. But if it's negative, we can take the modulus, and it will be negative. But if we add y again, it will be positive, and we're done. Cool. And semitone per octave, it will be really useful. It's just 12 semitone, and it will be more expressive this way, and we can reuse it. Great. So 2 new things interesting. The next thing is that we said that 2 notes that are separated by 12 semitones share the same name. And actually in music, it has a name. It's a chroma. The chroma is the name of the note without its octave, okay? So let's implement it. We will use it a lot. So a chroma is also a type that will contain a number of semitones. So it looks really like a note, but it will be different. So we have 2 different types, one for chromas, one for notes, so that we don't mix them. And we have 2 operations. The first one will be a plus operation like this. That will take, so the plus, that will take a chroma and a number C, and a number of semitones S, and it will do exactly the same as for the note, except that it will be doing it modulo number of semitones per octave. So we'll build a chroma, and its value is actually C plus S double modulo octave semitones per octave, like that. Yes, it will work. And another one, which is the minus, and this one will give us the number of semitones between 2 chromas. So we will have a chroma X and a chroma Y, and it will just make X minus Y and the whole thing modulo. Yes, thank you. Yep, like this, and a semitone per octave. Great. So now we can do some interesting calculation with the chroma, and yep, I didn't define these ones like that, and we're good to go. So now from there, we can do a bit more stuff. We can define our chromas. So it's easy. Let C, it's just chroma of with 0 semitone. So we just write it. It's our base. But next, we can see that D is, so this is C, and D is here. So it's plus 2 semitones. Okay, let's write it. So it's C plus 2 semitones. Great. And then E is actually D plus 2 semitones also, like that. Cool. And next, the next one is F, but F is not 2 semitones further. It's just 1 semitone further. So it's a bit different. F, E plus 1 semitone. And the next one are just plus 2 semitones, so J is F plus 2 semitones. And if you read music theory thing, you will find exactly this written, like J plus 2 semitones, and let B equal A plus 2 semitones. And if you make the computation, you will see that the difference between B and C will be actually 1 semitone. So like that, yeah. You know these notes, okay? So we just wrote this, and that's useful. We can check, define them for further use. And the next thing will be to do a small function that takes a note and extract the chroma. Okay, so if you give me a note, I will give you the chroma that corresponds to it. So it's really easy, chroma, and it just takes a note n, and it returns a chroma, so like that, and the value is just modulo semitones per octave. Great. And the next one, we'll test all that in a few seconds, you will see. The next one is doing the reverse operation. It takes an octave. So it will put the chroma to a given octave, so it will take a chroma N, a chroma C, and an octave O, and we'll just construct a note that is the chroma plus 12 times, so C O multiplied by the number of semitones per octave. Great. And after that, we can define our notes like being let big C equal octave of little c. Okay, so I take my C chroma, I use the octave function in it, and it will wait for the number of octave to actually create the thing. So C is not a value, it's a value because it's a function, and a function is a value, but actually it takes an int and will the octave and will return a note. So D is octave of D, and I will do just the same for E, F, G, A, B, and here the same E, F, G, A, and B. So now we can define any note given its name. Cool. Let's continue. This is a small pretty printer. I will show you, for instance, if I do something like it adds a printer for chroma and for a note. So for a note, like I take C3 and I just run it, and you can see that it will write C3 instead of the calculation of 12 by the number of semitones and things like that. Cool. So it will be easier to read this way. So now we can, you know, a sharp and a flat. So if you have a note and you try to take the sharp of it, you're just adding a semitone, okay? And a note with a flat is 1 semitone less, like that. So we can create this small unary operator plus and minus that will be flat and sharp by doing like, so this is the way to say that this is a prefix operator in F sharp. So I can prefix with a minus, and it will call this thing. And so it will take a chroma C and just do C plus minus 1 semitone, like that. And I can do the sharp, that will be like plus. That will take a chroma, and return it with 1 more semitone, like that, which is, if I say C plus like that, it says it's a C sharp. Cool. I prefer this one. It's F sharp. Thank you. And let's continue with that. Now, we need to talk about intervals, because once we will want to try to write some chords like major or minor, we will need the interval. So what is an interval? The interval is a distance between two notes. Okay, so for instance, the distance between these two notes is 0. It's what is called unison, okay? But the distance between this and this is two semitones, and it's called a second. And then there is the third, like that. Oh, and this one is a fourth, this is a fifth, this is a sixth, this one is a seventh, and this is the octave, which is in chroma equivalent to the unison, okay? So we will define a type interval, which is actually, we'll construct it as a function that takes a chroma and returns a chroma. So the meaning of this is that if you give it the first note, it will return the other note. So if you have a second and you give it a C, you will get a D. This is what we need. So we will define them. Let's diff. So we will apply a difference D to chroma. Yes, let's call it interval. It's better, interval. D is its distance, and we have a chroma C. We just return C plus D. So this way, so you can see that it will take a number of semitones and take a chroma and return a chroma, and this way we can create a unison function that is the interval between C and C, right? And we'll define the second, which is the difference between D and C, and the third, which is the difference between E and C. Yep, like that. And the fourth, which is the difference between F and C. And the fifth, J, the sixth, with A and C, and the seventh. So until now, you see that we are really reusing what we already wrote before a lot. I could have put directly the number of semitones here, but it's far clearer this way to use the concept we already defined before to actually apply them. So B. So for instance, we can just try the fifth for A, and I just need to that, and it's E. Let's try. So we have A, like, and then the E will be yes, this is the same difference here than between. Yeah, we can hear that the same difference. Cool. So it's working. It's a fifth. And let's continue, because now we need. We sometimes we take an interval and we take a minor version of it. So for instance, when we have a third, like this is the major third. Okay, like that. But we also use this one, which is the minor one. Okay, so I remove one semitone from the interval. So it will be quite easy to write. This is a function minor, which will take an interval. So it's we'll say that it's an interval. And what we will do is that this function also has to return an interval. So the way we'll do it is that it will take a chroma, C, and we will just pass the chroma to the interval, like that, and remove one semitone to the thing. Yes. So now we can take a minor third, like that, and applying to C, and see, yeah, it returns either, it could be either E flat or D sharp. So this is what I just showed you before. So yeah, minor third is working correctly, that's cool. So the next thing is to create a chord. So a chord will be defined with a chroma set, and so it will be just a set of the chroma will listen, because as you can see, in part of the music, it's not very, in guitar and ukulele especially, knowing in which order the notes and the chroma are inside the chord is not that important. So playing something like, which one is, I have some different version for the same chords. For instance, this one and this one sound the same, but it's not the same actual four chroma inside. Okay, so some are duplicated and some are not in the same order, and we don't care. So that's why we just use a set, which is a list that remove duplication. Okay, and since we have coma, it can be any octave, and for us it will be the same because the chromas. Okay, so we define a chord thing, chord, and it will just contain a chroma set. So as you see, we just reuse the vocabulary. A chord is a set of chroma. Great. And now let's write a function to build them. So the thing is that we create a small chord function that will take a list of intervals, okay, which will be the intervals to apply to fundamental chroma, and it will return the actual chord where all these intervals have been applied. So, for instance, the major chord is done with a unison like that, with a third, a major third like that, and a fifth. And just so that this one doesn't interfere, we'll put another C like that to the octave, which is equivalent to the unison. So this is a major chord. The minor chord for C would be with a minor third. So like instead of doing, we do. Okay, so let's play it. It's like, so you hear the difference. So let's build a chord. So here we have intervals, and it will take a chroma. So it's an interval list. And we just take the intervals. So we can just say something like for E in intervals. And we apply each interval E to our chroma C, and we get a list of all the chroma, and we just create a set from that and put it in the chord structure. What? Here? Yeah, here. Ah, yes. Sorry. Oops, chord. I get a bit lost. Each, just like, okay. Great, thank you. And so now we are able to define let big M will be for major, and it will be actually a chord of unison and fifth, third, and fifth, like that. And minor will be a chord of unison, minor third, So I'm just writing what I just explained to you on the instrument. I'm not doing far much than that. And we can just try it with C. It gives a C, a E, and a J. And if we try minor C, we'll get C, D sharp, and J. And if we try with E, it will be E, J, B. It's exactly what we want, so great. So next thing is about the strings. So on a ukulele, we have 4 strings. The first one is a J. The next one is a C. The third is a E and a A. So we just have to give a string its note, and we will do with that. But then we will create a fret type, which is the position where you put your finger on the specific string, and actually each fret is equivalent to a semitone, so we'll use our semitone unit for that. So type it, string, so it will overload the .NET string thing, but I don't use it, so I don't care. Yeah, let's go full domain-driven design. And fret is a fret of string and an int like that. So here they're almost defined like that. Cool. And the next part, I can define my 4 ukulele strings, which are G4, C4, E4, F4. So it's a bit strange on the ukulele, but the first string is higher than the two next. And here I will create a small function that take a string on a chroma, and that will tell me where to put my finger on this string to play the string. So let fret. So it will take a string, which has a note that we will call S, and a chroma C. And what we do is that, let's look at it. This is a C. So if I want to play a D, I have to put my finger 2 semitones between, because the difference between D and C is 2 semitones. If I want to play a D, C on a A string, I have to put on the third, because there is a difference of 3 semitones between C and A. And what if I want to play, for instance, a D on the E strings? I will have to put it near from there, because I cannot go below the start of the string. So I just make a modulus 12 operation, and I go from there. So it will just be C minus S, okay? And so I can create a fret structure with my string S and the number of semitones between C and S, and that will just tell me where to put my finger. Of course, this is not chroma, so I have to convert it to chroma, like that. And I can continue. And so I will return it as a list, because you will see in a few minutes this is to combine everything together. The next one is just doing a bit more. So it's called frets, and it will take a string S and a chord CH. And the thing it will do is that inside the chord we have several chroma, and we'll just apply the precedent function to each. So for C in CH, we'll just call the fret. So I take the chromas from the chord. So C is my chroma in my chord CH, and I call the fret function with my string S and the chroma C, and it will give me a fret list. Fret list because actually before I was returning a list. And the next thing is where we'll combine all this. So the thing is that on each string, I can play any of for instance, for C major, I can play all the chroma on the C string, like that. I can play them all. So, but it's true on every string. So it also works there. The only thing is that which is the most practical way to play them and combine them. So the thing I do is that you have a small ASCII schema there, which says that if I have a list that contains A and B, which are the two different chromas that are possible on the first string, and C and D, which are two chromas on the second string, it will create the list AC, AD, BC, BD, which combine the possibilities on each string together in new list. Okay, so I will not write it live because it's not very interesting, but as you can see, it's not very long. It's just doing this. And I will use the small dot operator to combine things together. And this way, I will be able to do this. So the phrase choices function will say, OK, let's combine on string A, on string J, and combine with string C, and combine this with string, the next one is, so oh yeah, I will take the frets on this one and combine them with the frets on C, and combine them with the frets on the third string, which is D, and E, and the last one, I'm almost there, with J. And this one will just enable me to enumerate all the combination for a chord. Yes, A. Yeah, thank you. To be that careful. It means that you understand what I'm trying to do, which is great. Like that, and it should work. It's not. And I have a problem there. Sec, frec, list, chord. This is what I expected, but. Okay, let's continue. I think I have just 1 minute left due to my problems precedently, so I will show you after. So the next function I will just explain to you because it will be faster. Sadly, you will not see the result of the demo. But the thing is that I will show you in the, yeah, I have all the code there. So I will show you the result because it will be faster. So that's exactly what I typed, but without the small mistake that I did at the end. Here I create a fret chroma function that takes a fret and just recalculate what is the chroma for a given fret. Okay, so it takes the string and the number of submittance, apply them, and I get a chroma back. Cool. And then tab chord is doing something. It's taking a list of frets, and for each it will extract the chroma, and we will make a chord back. So it will say that if you have a list of frets, we can try to see what chord it's playing. Okay, so if I'm playing that, like, I don't know the name of this chord, but I can get the set of chroma that I'm playing and compare it with what I wanted and see if it matched. Okay. And then there is this interesting function which is difficulty, and the difficulty takes a list of frets and make a sum of the distance to 0. Okay, and actually it's making a sum of the square. So the thing is that it says that it's easier to do nothing like that, but it's a bit more difficult when I have to press 1, and a bit more difficult when it's further, because if I have to do something like that, I won't be able to play it. Okay, so let's try to be closest to the start, but we can do more evolved difficulty function. And then this is a final function which says tabs, and it takes a chord, and what it does is that first it it enumerates all the possibilities to play the chroma from this chord on all the strings. Okay. The second line, so the filter, is taking the actual fret list and reconstructing the chord and check that it's the same one. Why? Because I could go in situation where things like if I do this one, it looks almost like a C major, except that there is no J. So it's not the same as this one. Okay, all the notes are inside the chord, but they are not all the chord chromas, so something is missing. So I filtered them out by just checking that we can get the chord back. And then I sort them by difficulty. I just take the first one. And we can try this. I will just run it. Let's restart this. And this is cool. I also add my pretty printer, which is really cool. Yeah, everything is running, great. And I can go back to my, for instance, here you can see the tabs. So that's the pretty printer for the thing. Yeah, it's just ASCII art. So for instance, Get Lucky is minor B, major D, minor F sharp, and major E. So it's, if I follow the instruction, I just put my fingers there, and then like that, and then like that, and then like that. Do you remember? That's cool. And I have another one which is really cool too. This is this one, and after that, I just take questions. And so this is this one. And you know this one, that's the theme song from Denver, The Last Dinosaur. So I'm in Denver, so this is a D, like that, and then A, and then J, and then A, and then D. So Denver, the last Denver, the last dinosaur is my friend, and a whole lot more. Denver, the last dinosaur, come from a world I never seen before. Thank you.